Hello everyone, welcome to The Biggest Ideas in the Universe. I'm your host Sean Carroll. This is the Q&A video for idea number 15, I think it was 15, which was gauge theory. As we said in the video itself, gauge theory was sort of a culmination, a summing up, a high point in which we were able to bring together the payoff of talking about quantum field theories and geometry and topology and scale and a whole bunch of other things in an interesting way. So the Q&A video is going to be, actually I think this is going to be an important and a good one. I mean, the questions on the blog post and in the YouTube videos were extremely on point. Let me put it that way. They were very good questions. And in part, I think that's a reflection of the fact that this is a very rich and rewarding topic where in the original video, I'm not able to cover everything interesting that there was to say about it. Now, there would be an obvious strategy to do here, which would be to have a separate video on the standard model of particle physics, because the standard model is the best theory we have for how the world really works, the quantum field theory world anyway, apart from gravity. But I'm not going to do that. I've decided not to do that because the standard model by itself is not one of the biggest ideas in the universe. It's on the one hand really, really beautiful and certainly extremely effective in fitting the data. On the other hand, it's a concatenation of a lot of different ideas from a lot of different angles. So basically for these videos, what I'm interested in is giving you the basic insights on the ideas themselves, the major concepts that go into building the standard model. So things like renormalization and symmetry and so forth. But for the actual standard model, many of the details are going to be left aside. They're interesting, they're well worth studying, and I encourage you to go do that. They're just not what we're about here in this series. So what that means is that I had the opportunity in this Q&A video to fill in some of the gaps between the gauge theory video and the actual details of the standard model. So let's get to doing that. One thing is this issue of mass in quantum field theory. I said something, the mass of a particle, the mass of a field. So we've said before that quantum fields, when you quantize them, they look like a collection of particles. So even though the mass of something is something we attribute to an object, something that can have a rest frame and you measure its mass in the rest frame, we often very casually talk about the mass of a field, by which we mean the parameter which, when you quantize it and when you get a particle out, will be the mass of that particle. So, but how do you know, if you look at a quantum field theory, what the mass of the particles is? So I said that the mass term comes from, if you have some field, I said, I think I did in terms of gamma, the photon field, but let's just simplify our lives and consider a single scalar field, okay? A scalar field with just a single real degree of freedom, as we say, phi of x and t. So at every point in space-time, there's a value for phi. It's a real number, the simplest possible field we can invent. So the punchline is the mass term is the term in the Lagrange density for this field, which looks like some parameter times phi squared. Okay, and that's what we want to try to explain a little bit. I'm not going to be able to explain it fully because you have to go through the details of quantizing it and you know, showing that there's a limit in which it looks like particles again, and so we've done that part. So I'm going to sort of hope that you just trust me in some of those details, and instead say, you know, why isn't phi to the cubed or something like that? What's so special about phi squared? So we know that we have the action. This is how we think about the equations of motion, the dynamics of this field, classically, and then we'll quantize it, etc. And the action is, we've done this a million times, I'm going to keep doing it because it's worth doing, the integral of Lagrangian, okay, dt, and the Lagrangian is the integral over space of the Lagrange density, and Lagrange density is a function of phi and derivatives of phi. So, of phi. And so therefore S, the way we usually think about it is the integral d for x, so the integral over all space-time or over some volume of space-time of this Lagrange density. And what is the Lagrange density, L? Well, it is the kinetic energy density, but I'm not going to bother with those niceties now. Usually when we just did point particles, we said kinetic energy minus potential energy. For a field, there's other kinds of energy that can come in. So we have minus the gradient energy, This is how the field changes from point to point in space, whereas the kinetic energy is how it changes from moment to moment in time. And then you have minus the potential energy. And there's another term which we could have had just for the point particle, which is minus the interaction energy. So the field is going to interact with other fields, and that's going to contribute to its energy, and that's going to contribute to its equations of motion. Okay, but let's ignore that for right now. Let's just think about fields all by themselves, just a scalar field all by itself. Well, let's look at some of the details here. The kinetic energy, as it turns out, is 1/2 phi dot squared. Phi dot. In fact, phi dot might be notation I may or may not have used. I forget. It's the time derivative of phi, okay? d phi dt squared. So literally how fast the field is changing in time, that's squared times 1/2. I'm not going to justify this, but it doesn't seem surprising. The kinetic energy for a particle is 1/2 mv squared. V is the velocity. So it's 1/2 m dx dt squared for a field. Replacing dx dt with d phi dt does not seem like a big stretch. Where did the m go, if you want to know? Well, it kind of got absorbed into the definition of phi when we relate phi to particles. Gradient energy, so it turns out, this is actually a very nice thing. We didn't go into details here, but we know exactly what the gradient energy is going to be even before we do anything because of relativity, because of special relativity. Special relativity says space and time are on an equal footing. So if this is what the kinetic energy is, we instantly know what the gradient energy is. It's minus 1/2 derivative of phi with respect to space squared. Now, I'm just writing d phi dx squared. It's really d phi dx and then squared plus d phi dy squared plus d phi dz squared if you're in 3 dimensions, but you get the point. It's the rate at which the field is changing over space squared. So what about the potential? We'll just write v of phi, okay? So this is what we have to work with. So when you write a scalar field theory, the kinetic energy and the gradient energy basically are fixed. Those are universal. Those are what we have for every scalar field. That's not always true. Cosmologists like to mess with the kinetic term in interesting ways, but we're not going to do that. Usually what you get to play with are the interactions and the potential. Those are the things that come into your definition of what you mean by this scalar field theory, okay? So what is the potential going to be? Since we're ignoring the interactions, what is v of phi going to be? Well, what you can do is, remember the whole thing that the whole philosophy we're taking towards these quantum fields is perturbative. That is to say, we're imagining you start with the vacuum state, with a state with no particles, the field just sitting there very, very quietly, and then you perturb it a little bit, okay? You let the field vibrate very, very gently. You don't have to do that. You can imagine, the field fluctuating very, very wildly, but here on Earth, even in a big particle accelerator, most of space is just empty. There's a few particles. Most of the modes of any particular quantum field theory are in their vacuum state. So this idea that you start with the vacuum state and then add a few vibrations is a very good model to what we actually have in the world, okay? So therefore, when we do this v of phi thing, we can imagine that phi is small, right? If we imagine that phi equals 0 is the minimum of the potential, is the vacuum state, is the classical vacuum state, then we can look at small variations of phi. So you might say that v of phi, well, it's going to look like, I'm going to draw a squiggle there, so we don't need to worry about the parameter, the specific numerical coefficients or anything like that. You might say it'll be, phi to the first power, plus phi to the second power, plus phi to the third, plus phi to the fourth, etc. Okay, that kind of expansion, and these terms should become less and less interesting, less and less important as time goes on. And the first thing to notice is that, in fact, you're not going to have a term proportional to phi by itself, linear in phi, because if you did, that would mean that the potential, v of phi, as a function of phi, what does this look like in general? Well, that phi term means that the potential has a non-zero slope at phi equals 0. And then, it goes on to do whatever it does, depending on what the other terms are. But the point is, if that were your potential, the field would just roll down to the minimum, okay? So you're not actually at the minimum. If you were at the minimum, you can't have a term proportional to phi there. If you're slightly more happy with calculus, the way of saying this is, at the minimum of the potential, the derivative of the potential has to vanish. So the coefficient of phi has to vanish. So in fact, let's get rid of all of this. There you go. So we have a term proportional to phi squared. That's the very first thing that appears. And then phi cubed and phi fourth and so forth. Now phi cubed and phi fourth are different in an important way from phi squared, in a few different ways. For one thing, you notice that if you look at the kinetic term, it is phi and it's squared, right? It's the time derivative of phi squared, but it's still, there's one appearance of phi to the second power, so there's basically two appearances of phi in the kinetic term. Likewise, there are two appearances of phi in the gradient term, right? d phi dx squared. So this first term, phi squared, in the potential, kind of goes along with those. It's the same order of phi in the equations. And that actually has an important consequence. So let's imagine that we only have phi squared. Let's imagine for the moment that let v of phi be something, which I'm going to precognitively, I'm going to predict the future. I'm going to say, let's let this be 1/2 m squared phi squared. Okay, let it just be that. Okay, nothing else. Then the whole Lagrange density looks very sort of nice and similar, right? 1/2 d phi dt squared plus 1/2 d phi dx squared plus 1/2, oops, minus, I need some minus signs here, minus 1/2 d phi dx minus 1/2 m squared phi squared. So phi appears twice in every single one of these. And remember how we got the equations of motion. The equations of motion come from minimizing the action. You knew that was going to happen. Talking and writing at the same time, not my strong suit. So by the way, let me say, this Q&A video is going to get a little more technical than the regular videos. I know you might think that the regular videos are already technical, but I'm going to use this Q&A video when we can let our hair down as an excuse to get a little bit more into the weeds here. It's just inevitable. So I'm going to be writing even more equations than I usually do. So the equations of motion come from varying or differentiating, the action and setting that equal to 0. So you're taking the derivative, and that's the derivative with respect to phi, right? That's the idea. You change the value of phi, the trajectory phi is on, the field configuration of phi, and you ask for what is the field configuration of phi that minimizes or extremizes the action as a function. So therefore, and that's going to lead to equations that you get, there's some details I'm skipping here, but you get that equation from the Lagrange density. And so if the Lagrange density, which is what goes into what gets integrated to give the action, is of order phi squared, right? If it has phi squared in the kinetic term, the gradient term, and the potential term, and that's all it ever has, then the equations of motion will be of order phi. They will all be linear in phi because you're going to get them by differentiating. I'm not going to write down what they are now. Well, we could write down what they are. The equations of motion for this particular Lagrange density work out to be, what are they going to work out to be? When you take the derivative of something squared, you bring down a 2, and it's going to cancel the 1/2. That's why all these 1/2s are there, because you're going to eventually take the derivative of them. But then you get a second derivative instead. So we're going to get d squared phi dt squared minus d squared phi dx squared minus m squared phi equals 0. Okay? This is the second derivative, this notation, d squared phi dt. That's just the derivative with respect to time of the derivative with respect to time of phi. Okay? So this is the equation of motion for that Lagrange density. I'm not going to tell you why, but you could look it up. And you notice that every term has one appearance of phi in there. These squared terms here, this d squared, that's not phi squared, that's the derivative. That you're taking the derivative twice. But phi itself, in every single term, only appears once, okay? Why? Why do we care about that? Because that means we can solve it. That means this equation is exactly solvable. And in fact, we sort of secretly did solve it. By solvable, many of the differential equations in theoretical physics are complicated. Einstein's equations are horrendously complicated. typical equations for an interacting quantum field theory, horrendously complicated. That's why we invent Feynman diagrams as a simple calculational tool that lets us approximate the answer. We're very, very happy if we ever find equations of motion we can solve exactly, right? This you can solve exactly. So by solvable, I mean we can get exactly what the answer is. And turns out the answer can be written, you can look at modes of this is a free quantum field. If you look at this equation, there's no interactions in it except for this phi squared. And what I'm telling you here is that phi squared, so v of phi equals 1/2 m squared phi squared, is not an interaction. Strictly speaking, it's part of the free theory. So we made a big deal when we did our original discussions of quantum field theory about starting with free fields and then adding interactions to them. And the free fields, the reason why we could do that is because the free fields had equations of motion that were solvable. Here it is. This is the equation that is exactly solvable and gets us a free field. And basically the solutions are, I'm not going to write them down because the chances that I get all the i's correct, etc., are very small, but they're plane waves. They're plane waves with a certain frequency and a certain momentum moving in some direction, okay? They're the modes of the field. Those are the exact solutions to this equation. And they have a relationship that the energy, really the energy density, but you know what I mean, squared equals m squared plus the momentum squared, where m really is this, okay? So this looks just like the energy equation for a particle, and that's not a surprise. That's not a coincidence. That's actually really what is going on. So that's why, I know I'm skipping steps and asking you to believe me a lot, but that's why phi squared, or field squared, is what gives you the mass of a field, because field squared in the Lagrange density corresponds to equations of motion that are still exactly solvable. So even if you have the kinetic energy, gradient energy, plus phi squared, you can solve them. That's what gives you the equations of motion for the free field. And then you add on to v of phi, lambda phi cubed plus eta phi to the fourth plus etc. And these will be interactions. Once you have those in your theory, you can no longer solve the equations of motion exactly. Instead, you use Feynman diagrams. And guess what? Phi cubed will give rise to Feynman diagrams that look like that. Phi, phi, phi. Phi to the fourth will give rise to Feynman diagrams that look like this. Phi, 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 etc. That's why, that is hopefully convincing you enough of why it's phi squared in particular that gives you the mass term. It's part of the linearized equations. It gives you this relationship between energy and momentum that we're very familiar with from particle mechanics, and it does not count as an interaction all by itself. So we can think of free fields as either being massless, if there is no phi squared term in a potential. Maybe there's higher order terms, but that's okay. Or they're massive if they have this term. So you see that this structure here for the Lagrangian is very, very general, because even though there will be, in general, many other terms in the Lagrangian, you will always start with these, okay? You'll start with the kinetic energy, and remember, the time energy, time derivative, and space derivatives are related by special relativity, so that's really sort of one thing that's going on. And you always have a phi squared term. You never have a phi term, because otherwise you wouldn't be at the bottom of the potential. And these are the two things you have. You have the kinetic energy, and you have the mass. Those are the two parts of defining your free theory. Okay. And that's going to be true for everything, so not just for scalar fields. When you get to gauge fields, when you get to fermions like the electron or the quarks, it's always going to be field squared in the Lagrangian that corresponds to the mass. And this parameter m really is the mass of the particle, okay, of the particle once you go to that particle description. Now, one of the reasons why I wanted to talk about this, well, I should have talked about it before. I mean, it is part of understanding what's going on. But also, you've heard that in the standard model of particle physics, masses come from the Higgs boson. And I wanted to explain a little bit about what that is about, because number one, it's not at all obvious why that is true. Number two, it's not even true, right? I think we already said that in protons and neutrons, most of the masses come from QCD, come from the strong interactions, come from the gluon-mediated interactions inside the protons and neutrons. But some of the masses, the mass of the electron and the masses of the individual quarks, for example, do come from the Higgs boson. I wanted to explain that because I didn't really get to do it. So think about spontaneous symmetry breaking again. Oh, I guess one question, which I'm sure it was asked, but I forgot to write it down, was why spontaneous symmetry breaking? Like what counts as non-spontaneous symmetry breaking? The answer is that non-spontaneous symmetry breaking would be explicit symmetry breaking. So if you simply wrote down a theory in which most of the terms in the Lagrangian had a certain symmetry, but one didn't, so the theory as a whole just doesn't have that symmetry, that's an explicit symmetry breaking. Spontaneous symmetry breaking is when the theory has the perfect symmetry, but the state the theory is in, typically the vacuum state the theory is in, violates the symmetry, okay? So like here on Earth, this is an analogy. This is not exactly the same thing, but here's the analogy. Here on Earth, if I drop the pen, it goes down, right? There is a spontaneous breaking of rotation symmetry. If I'm out there in space, the Earth is not there. If I'm closer to the true vacuum, then every direction seems exactly the same. But here on Earth, the existence of this planet below me spontaneously breaks rotational invariance. It picks out a preferred direction called down. Okay? So spontaneous symmetry breaking happens when the configuration of the fields breaks the symmetry, even though the theory itself, in its equations of motion, is completely invariant. So that's what we have in the standard model of particle physics. And let's pick a very simple example of an SO2 symmetry. Remember, SO2 is just a circle, right? It's just one thing. It's just rotations in, let's say, phi1, phi2 space, okay? And I'm drawing it this way because then I'm going to draw the potential v of phi1, phi2. And SO2 is just rotations in phi1, phi2 space. It's topologically and mathematically equivalent to U1. So if we defined phi, capital Phi, to be a complex valued field, phi1 and phi2 are real valued fields, but we could define capital Phi equals phi1 plus I phi2, right? And then there's be a U1 symmetry, e to the I theta phi. You just multiply, and that's rotating that phi. But we're not going to do that right now anyway, even though that is what we get in the standard model, but we're not going to do it for our purposes right now. Okay. So now we're imagining that we have a potential v of phi, 1, phi 2, that implements spontaneous symmetry breaking. So what that means is that the quadratic term, the phi squared term, will be negative. So what we want is the Mexican hat potential. Okay, the famous Mexican hat looks something like this. And there is a brim of the hat at the bottom here, which is the vacuum manifold, the place where the field will live with zero energy. And to get that, long story short, you write something like minus 1/2 mu squared phi squared plus lambda phi. Oops, I should be more explicit here because we have two fields. So this is phi 1 squared plus phi 2 squared. Then I got this wrong in the actual video last time, but plus lambda, and let's get it right, phi 1 squared plus phi 2 squared squared. Okay, so morally this is phi to the fourth, but this is written in such a way that it is actually invariant under the symmetry. Okay, and so I wrote mu squared rather than m squared because this would be the mass term for these two fields if the field were living up there, right, at the top of its potential, where phi 1 equals 0 and phi 2 equals 0. But if it were there, it wouldn't just live there. It would roll down to some point down here on the brim of the hat in the vacuum manifold. So mu squared here is a parameter of the potential, but it's not the mass. What you have to do is expand the field around the place it's actually living, okay? And in fact, let me move that dot. Let's put the dot over here, okay? Let's imagine that the field is at phi 1 equals 0, phi 2 equals something, okay? So what you should get from our previous discussion is that I don't know if I drew the potential here. Maybe I didn't even draw the potential here. But after saying that v is 1/2 m squared phi squared, what does that look like? It looks like just a parabola, right? V and phi. And so even if there are higher order terms, phi cubed, phi fourth, etc., the first term you're going to notice looking at tiny deviations from 0 is the phi squared term, okay? So that works even when the potential is more complicated, but you're not at phi equals 0. You can re-expand the potential here near the bottom into phi squared plus phi cubed plus phi fourth, etc. You can rewrite it by shifting and changing variables. That's a very easy thing to do. So that will be, so the mass of the actual field is not mu in any sense. It's some combination of mu and lambda that you get by changing variables. Okay, you can do that. But that's one thing you can do. The other thing, actually, let me draw it this way. So there's basically this thing that the field can do. It can oscillate back and forth perpendicular to the direction, to the radial direction, along the radial direction is what I should say. So away from phi 1 equals phi 2 equals 0. That kind of oscillation would be a massive I almost said gauge boson, a massive boson. There's no gauge theory here yet. We're just doing a global symmetry, okay? There's a massive boson corresponding to oscillations that go up and down in this brim of the Mexican hat by going radially either inward or outward from the origin, okay? It looks locally like phi squared is not 0. And in fact, it is if you change variables. But there's another direction you can go. You can also look at oscillations around the brim of the hat, right? Hard to draw here in a very convincing way. But you can look at oscillations that stay in the vacuum manifold. These are the sort of the two perpendicular directions, starting from this place where you're in the vacuum manifold. That's the value the field has. You can sort of oscillate in two different directions. And what you notice is, along the brim of the hat, it will always be true that the mass is 0, because the mass is the coefficient of phi squared, and there's no potential along that brim of the hat. The potential in that direction and only in that direction is 0. It's flat. So this is a massless boson. So if you had just had both the coefficient of phi squared and the coefficient of phi to the fourth be positive, then you would have the minimum would be at the center of the potential, because everything would be going up, okay? The minimum would be at the bottom. Both oscillations would be a positive mass, because you would have curvature of the potential that was positive in both directions. But because of this spontaneous symmetry breaking phenomenon, you have one of the directions in the potential gives you a mass, but the other one is massless. And it is always true because of the symmetry. There's always a direction in field space where the symmetry relates what happens to what happens at one point to what happens to another point. You notice that the brim of the hat, every point is related to every other point by doing an SO2 transformation, by rotating around in field space in that way. And because it is a symmetry, nothing can change from one point to another, and therefore the potential cannot change from one point to another, and therefore the potential is flat, and therefore the mass is 0. So that's a theorem. That is called Goldstone's theorem. Although Goldstone definitely came up with the theorem, but the idea predates him a little bit to Yoshiro Nambu. So these are often called Nambu-Goldstone bosons, these bosons that are in the flat direction. Goldstone's theorem says that spontaneous symmetry breaking, which I will now... spontaneous symmetry breaking for global symmetries... So this is not yet a gauge symmetry. This is just two fields which I universally rotate everywhere. Always leads to massless bosons. This was a big worry when people invented this. This is like the 60s when people are thinking that, Nambu and Goldstone and others, because they liked the idea of symmetries. They had noticed, Nambu especially, was a pioneer for understanding symmetry breaking, spontaneous symmetry breaking, But then there's a theorem that comes along that says when there's symmetry breaking, there is a massless particle. The thing about massless particles is they're easy to make, right? They don't cost any energy to make them. That was another question that was asked. Why doesn't it cost energy to make massless particles? When I say it doesn't cost any energy, what I mean is it takes arbitrarily small amounts of energy. If you have a mass, there's a minimum energy that you need to make, E equals mc squared, to create that particle. If you have a massless particle, for any fixed momentum, a wave or a particle in that field still has energy, but since the momentum can go to zero, the energy it takes also goes to zero. So there's no lower bound on what the energy is. So we don't see Goldstone bosons in the real world. We see approximate Goldstone bosons. There's a whole discourse about pseudo-Nambu Goldstone bosons, PNGBs, for symmetries that are broken explicitly as well as spontaneously. But this line of reasoning was thought to be bad news for fans of spontaneous symmetry breaking, since we don't see any Goldstone bosons. Okay. Well, it turns out I've been emphasizing that this is for global symmetries because it turns out the story is very different for gauge symmetries. And I hopefully this discussion for global symmetries made sense and you understood it. You understand that one direction in field space is flat, therefore massless bosons. The perpendicular direction is curved, therefore massive bosons. Once you get to the gauge symmetries, it's much harder to actually go through the details in this way, so I'm not. What I'm going to do is tell you the answer. Okay. So for gauge symmetries, well, you start with some massless bosons, right? You start with not scalar bosons, but vector bosons, the spin 1 particles that are actually carrying the gauge symmetry, right? The force bosons, the photons, the gluons, the gravitons, or what have you, okay? So you start with, so pre-spontaneous symmetry breaking, you might have massless spin 1 bosons, and maybe you also have some massive scalars. Okay, so if we had a theory like this, but it was all pluses in the potential, so there was no spontaneous symmetry breaking, the minimum was just at 0, you could have some massive scalar fields that would give you massive scalar bosons, and they could be coupled to some gauge potentials, right? So in this case, in this theory that we have right now, it's an SO2 symmetry, so that's the same as a U1 symmetry, so we'd have the equivalent of photons. So this would be a kind of photon-like theory. And those would be your massless spin 1 gauge bosons. And then you have some massive scalar bosons. Let's say this is without, so no spontaneous symmetry breaking. Then you have with spontaneous symmetry breaking, what happens is the colorful language that we use is that the gauge bosons eat the Goldstone bosons and get fat. They get massive, okay? So you get massive spin 1 bosons. So in this case, by the way, let's stick with this theory. Without spontaneous symmetry breaking, what we mean is the potential looks like this. If you did not have spontaneous symmetry breaking. So here's V of phi, phi 1, phi 2, and we're imagining that it's plus phi squared plus phi to the 4th, okay? So you have, guess what, 2, can I move this? Yeah, oops, no. Always forget what I can do. Oh yeah, look at that, I did it. 2 massive scalars, 1 massless spin 1 boson, if you have an SO2 gauge theory, the photon, basically. With spontaneous symmetry breaking, what you have is a massive spin 1 boson and 1 massive scalar. So this is the case where the potential looks like the Mexican hat. Very sloppily drawn Mexican hat. So the direction that is along the flat part, the vacuum manifold, is now eaten by the gauge boson, and it becomes massive. So the point is, another way of saying this, I know I'm skipping over a lot of things. There's just too much stuff going on here. A massless gauge boson, well, a massless spin 1 boson, let's say. I'm glossing over one of the facts is that except for gravity, which is weird, all the gauge bosons, the force-carrying particles, have spin 1. We haven't even talked about spin yet, but you're just going to believe me for right now. A massless spin 1 boson has 2 degrees of freedom. And what does that mean? Well, we talked about degrees of freedom. A degree of freedom is, how much information you need to tell me to fully specify what's going on. So if I have one single scalar field filling the universe, I say I have 1 degree of freedom, if it's a real scalar field. If it's a complex scalar field, or if it's 2 real scalar fields, I have 2 degrees of freedom. A massless spin 1 boson is 2 degrees of freedom, and basically the way we think about that is if you're moving, so if this is the momentum of the boson, then it has spin, and it can either be spin this way, okay, spinning right-handed compared to where you're moving, or it can be spinning this way. Those are the 2 choices. So it can be spinning right-handed or left-handed. Right-handed or left-handed circular polarization for you classical electromagnetic fans out there. So the spin can be either along the axis or opposed to the axis. And those are the only possibilities because when the boson is massless, it has to move at the speed of light. For a massive spin 1 boson, it doesn't have to move at the speed of light. So there are 3 degrees of freedom. And that's because there is also the particle is spinning perpendicularly to the direction of motion, or I should say the motion is not even defined. So if I go to the rest frame, I could imagine it's spinning this way, or spinning this way. You might say, why can't it spin that way? Well, because this is supposed to be symmetric around this circle, so spinning perpendicularly that way is just the same no matter how I orient it. I know that's not completely convincing. That's because we haven't talked about spin yet, but this is the true thing. The point is that with spontaneous symmetry breaking in a gauge theory, you don't get Goldstone bosons ever. What you get are massive gauge bosons. So you've sort of been glancingly referred to this in the case of the standard model, right? What do we have in the standard model? The standard model of particle physics. We know that it's based on a symmetry SU3 cross SU2 cross U1. And that symmetry is spontaneously broken via the Higgs mechanism down to SU3 cross U1. Now you might think that what that is saying is that SU2 is broken and the rest are left unbroken. It's not quite that simple. The SU3 that you get, the strong interactions SU3, is just still unbroken. Okay, it's just left unaffected by the Higgs boson. But the Higgs boson affects both SU2 and U1, and it breaks them both, but it leaves this U1 invariant. Okay, so it leaves a U1 behind. Morally, it's equivalent to just breaking one SU2's worth of symmetry, but this is what actually happens in the real world. I want to be telling you what actually happened. So we're not going to go through the details, but we're going to count degrees of freedom. That's something we can do. The numbers are small. They do not require a lot of arithmetic talent. So you're breaking SU2 cross U1 down to a single U1, so it's kind of like the U1 just goes along for the ride. It really doesn't. It's more complicated, but let's pretend that it does, okay? So it's like you're breaking SU2 to nothing. It's like you start with an SU2 symmetry, gauge symmetry, and you completely break it, okay? So what is SU2? SU2 is almost, again, sort of morally, it is almost SO3. It's a 3-dimensional group. Okay? And what that means is, therefore, there are 3 gauge bosons. Okay? this is before symmetry breaking happens. So let's just say there are 3 gauge bosons. That's all we will do. But then you also have the Higgs, which is a complex doublet of scalars. This makes sense because it's SU2, right? So the Higgs, let's call it H, can be written H1, H2, where both H1 and H2 are complex valued fields. So this is 1, 2, 3, 4 degrees of freedom because these are complex valued fields. Every complex scalar field has 2 degrees of freedom, and these are 2 complex valued fields. Okay, so 4 degrees of freedom overall. So it's, again, I can't really draw 4-dimensional space, but it's kind of like I can draw 3-dimensional space. So if I had a 3-dimensional set of fields, phi 1, phi 2, phi 3, I don't. I have a 4-dimensional set of fields, but I could imagine that the potential would be minimized on a 2-dimensional sphere, right? That would be the equivalent. This would be a 3-dimensional Mexican hat. And so the vacuum manifold would be these points on this sphere. And I would have a number of degrees of freedom that would be along the sphere, okay? And those would all be Goldstone bosons in the global symmetry breaking case. And this is not a very good representation because I'm only able to draw 3 of them. But the point is, these 4 Higgs degrees of freedom, DFs, degrees of freedom, after spontaneous symmetry breaking, go to 1 massive scalar boson plus 3 massive gauge bosons. So if the symmetry were global rather than a gauge symmetry, there would be 3 Goldstone bosons from the spontaneous breaking of the Higgs by the Higgs of this symmetry. There'd be 3 directions you could move the field that would keep it in its vacuum manifold. This, by the way, is why there are no... Sorry, I don't know where to draw this. Let me just say it in words. This is why there are no cosmic strings or monopoles or domain walls in the standard model of particle physics, because the vacuum manifold is a 3-dimensional sphere. That's why you get 3 massive gauge bosons, 3 Goldstone bosons, 3 what we say would be Goldstone bosons if they hadn't been eaten by the gauge bosons. And a 3 sphere has no pi 1 or pi 2 or pi 0, no non-trivial first, second, or 0th fundamental group, so no strings, monopoles, or domain walls. There you go. Sorry about that. But anyway, this is what you actually have in the standard model of particle physics. These should be familiar. 1 massive scalar boson, we call it the Higgs boson. That is what we discovered at the Large Hadron Collider in 2012. 3 massive gauge bosons, which we call the plus W particle, the minus W particle, and the neutral Z particle, the Z naught, okay? These are 3 gauge bosons that were massless before symmetry breaking. They ate up the Higgs boson and they got fat. And this is why the weak interactions are short range, because these fields that carry the weak interactions are massive. If you go way back up to this equation of motion that we had right here for massive scalars, you could say, well, let's change the right-hand side by adding a source, okay? By adding some particle that creates, that couples to this phi field. And what you find is, oh, this is something I got wrong last time. What you find is a Yukawa potential. So the potential for this, I'll just write it in a different color. So the field value, what can we say here? If we plot as a function of distance from some source, the value of phi, I'm using the word potential in 2 different senses here, that's why I'm hesitating, but it goes down exponentially, okay? It goes e to the minus m times r, with this value of m right there, okay? I said that the force went like e to the minus mr, but that's not right. The force is the derivative of this field value, so it actually goes as e to the minus mr over r. Just to be very, very careful. There you go. The point is that this fades away very, very quickly as r gets large compared to the inverse mass, compared to the Compton wavelength of the particle. So, because the Compton wavelength is 1 over the mass of a particle. So when you have these massive gauge bosons with the masses are very roughly 100 GeV. It's more like 85 and 90 or something like that, but still, of the order 100 GeV, that's a very big number. The Compton wavelength is a very small number. The range over which the weak nuclear force is noticeable is very, very tiny. That's one of the reasons why neutrinos can just pass through your body all the time. Neutrinos can pass through the Earth all the time because neutrinos don't feel the strong nuclear force. They don't feel the electromagnetic force. They're neutral. They do feel the weak force, but the weak force is really weak. You have to get really, really close to something before you feel the weak nuclear force, and this is why. Okay. So I'm not sure how convincing that whole discussion was, but the point is, this is actually, so I haven't even gotten to how electrons get mass yet, right? A lot of people, you'll hear people say that the Higgs mechanism was invented to give masses to the electrons or the quarks or whatever, which is completely false. No one knew, certainly Higgs and Brown and Engler and the others who were thinking about these ideas in the early 1960s, they had no idea that you could use the Higgs to give masses to fermions, to electrons and quarks and things like that. They thought that you could what they cared about, which was true, is that you could spontaneously break a gauge theory and make it go from being long range to being short range, okay? And the reason why they cared about that is because they weren't even thinking about the weak interactions. They were thinking about the strong interactions. They didn't know about QCD. They didn't know about asymptotic freedom or confinement or quarks or any of those things. What they knew was it seemed like an attractive idea to make the strong interactions a gauge theory, but gauge theories gave 1 over r squared forces, and the strong interactions were short range. That's why they invented the Higgs mechanism. They thought that the strong interactions would be governed by a theory like this, and that's why it was short range. Didn't work out that way because nature is very complicated and tricky. But anyway, this is the explanation for why the gauge bosons in the Standard Model have a mass. It's because the Higgs mechanism gives it to them. They've eaten up the Goldstone boson. So this is supposed to explain both why there are no Goldstone bosons and why there are massive vector spin 1 bosons in the Standard Model. Okay, so what about the electrons? Why do they get their electrons, etc., in the Standard Model? What does the Higgs boson have to do with them getting mass? Again, I'm going to be a little bit technical, which means, in this case, sketchy. So usually when people say they're being technical, they're going to flood you with details. What I mean is I'm hiding the details from you, but just saying words that are true, and you'll have to go fill them in. So this is, again, Higgs and Brown and Engler, who shared the Nobel Prize for this. Also, Guralnik, Hagen, and Kibble wrote important papers about this. Phil Anderson wrote important papers about this. Nambu had thoughts about it. Tuft had thoughts about it. Mostly in the 60s, they were thinking about the strong interactions. It was Steven Weinberg in the late 60s who wrote this charming paper, very short paper, and the title was just A Model of Leptons. And he was trying to explain different features of the leptons. And one of the features of the leptons, like electrons, is they violate parity, okay? They act differently. There are right-handed leptons and left-handed leptons, and they seem to behave differently. Very roughly speaking, the weak interactions tend to interact with the left-handed leptons, but not the right-handed leptons. They act with left-handed particles and right-handed antiparticles, okay? But right-handed particles and left-handed antiparticles are just not doing anything in the weak interactions. And so Weinberg was trying to understand this. And what you would guess, if you were clever enough to know the underlying particle physics, what you would guess is left-handed electrons have a gauge symmetry of some sort, right? As we now know, it's an SU2 gauge symmetry. And right-handed electrons don't. So you can just say that. That would explain how electrons could have this interaction with the weak interactions. But the problem is the mass term for an ordinary electron, if you're Paul Dirac and you're writing down the Dirac equation, and you think about the mass term for the electron, I said that, all mass terms are field squared, right? Phi squared or gamma squared for the photon or whatever. But for fermions, it's a little bit trickier. It's still field squared, but it's actually the right-handed field times the left-handed field. very roughly speaking, okay? So the mass term actually looks like psi bar psi, if psi is the field. Let's call this psi e, so this is the electron field. Or this is what you would guess it looks like, mass times that. It's actually only mass to the first power, not the second power, because fermions are weird and different, but different than the scalar fields. But okay, here you go. And it turns out when this bar is like a complex conjugation kind of operation, but it also flips right-handed with left-handed. So if you have a symmetry that has an effect on the left-handed field but not the right-handed field. So this is, again, morally it's not exactly right. This is kind of like psi right times psi left. Okay, not exactly right, but okay, close enough. If psi left has a gauge symmetry and psi right doesn't, which is what the data seemed to imply in the weak interactions, then you can't write down this term. So this was a known problem. Like if you have a symmetry that affects left-handed particles differently than right-handed particles, then you're not going to be able to have a mass for any of those particles, not just the gauge bosons, but even the fermions that are related to those particles. So what Weinberg realized was that what you could do is, with the Higgs boson, remember we have this doublet here, right? Capital H, H1, H2. So what you could do is, you could write down the right-handed electron, so psi electron right, which is just a single thing all by itself. You could multiply it by H, which is this doublet of Higgs fields, and then you have a doublet of electron and psi e L, and the neutrino, psi nu L. So in other words, what Weinberg says is maybe deep down in the bowels of the standard model of particle physics, there is a symmetry relating electrons to neutrinos. They're a doublet under an SU2 symmetry. The left-handed ones. The right-handed ones don't have that symmetry. They're just single all by themselves. But what you can do is you can make a interaction term, not a mass term, but an interaction term with the Higgs boson. And then what happens is, for spontaneous symmetry breaking, let's write it this way, under spontaneous symmetry breaking, the Higgs field, which is a dynamical field that can fluctuate, gets the form some fixed value v and then 0 plus fluctuations. So this is the sort of equation way of saying that, you know, the field in its Mexican hat sits there at some value v, okay? So the first component of the Higgs field takes the value v, the second component is just 0. And what that means is that this term here starts looking like psi er v times psi er times psi el, which is just the mass term for the electron. And there is no corresponding term for the neutrino. And that's why neutrinos are massless in the simplest versions of the standard model, because there's no right-handed neutrino to do anything. Quarks are more complicated, but anyway, everything is more complicated. This is why I'm not doing a whole video on the standard model. But the point is, Weinberg realized that the Higgs mechanism, which was invented to solve the strong interactions, could be applied to the weak interactions and would explain not only why the weak interactions were short range, but also how you could have a gauge theory that affected left-handed particles but not right-handed particles, and yet still have those particles be massive through the genius of spontaneous symmetry breaking. So this was not the original reason why the Higgs boson was invented, but roughly speaking, this existence of the Higgs vacuum expectation value, the Higgs field has a non-zero value out there in space. The electrons are able to react against that value of the Higgs boson in empty space and thereby get a mass. It's a completely separate mechanism from how the gauge bosons get a mass, but it is nevertheless true at the end of the day that the Higgs mechanism gives a mass to both the gauge bosons, W plus, W minus, and Z of the weak interactions, and the fermions of the weak interactions, the electrons, the muons, the tau, and all of the quarks. Okay. I understand that there's too many details being glossed over to really get that, but I wanted to say a bunch of true things that by following all these videos, you are in a position to at least kind of understand in a way that, I wrote a whole book about the Higgs boson and the Standard Model particle at the end of the universe, and I couldn't quite explain things in this much detail there, so you get more than they would get. Okay. Anyway, lesson how mass comes in the Standard Model from the Higgs boson. And as we said before, protons and neutrons get mass from a completely different mechanism, but the quarks inside them do get mass from the Higgs mechanism exactly like this. The other thing I wanted to say about the Standard Model is people, I don't know what street corners you people are spending time on, but I made a plot something like this with energy, and I plotted the running of the coupling constants, right? As you go to higher and higher energies, the strong interactions get weaker and weaker. That's called asymptotic freedom. Asymptotically, as you go to high energies, the particles just become free. They're not interacting. The interactions get weak. So, whereas for electromagnetism, the interactions actually get stronger. So, in the Standard Model, SU3 cross SU2 cross U1. In the Standard Model, there are 3 different coupling constants. One for U1. You're tempted to say it's electromagnetism, but it's not. Remember, in the Standard Model, the actual U1 that you get for electromagnetism is not the U1 you started with when you say SU2 cross, because there's a admixture of SU2 and U1. So this is actually U1 hypercharge. I'm writing that very tiny so no one can read it because I'm not telling you what the details are, but just trying to get it right, just trying to say true things. So this is the U1 hypercharge, and it has a coupling constant, alpha 1. And there's a coupling constant for the SU3 bit, alpha 3. And there's also a coupling constant for the SU2 bit, alpha 2. Okay? And what you see is if alpha 2 and alpha 3 are going down, and alpha 1 is going up, maybe they all meet at some high energy scale, right? Maybe they're converging on each other and they can somehow meet each other. This is not an original idea. This idea, actually, Steven Weinberg and others talked about this in the early 70s, and this was put to good use by Howard Georgi and Sheldon Glashow in the mid-70s when they invented grand unification. So this is the idea that at this energy scale, near where they meet, grand unification occurs. This is an idea from the 70s. It may or may not be true. But if you have all of the gauge groups of the Standard Model, SU3, SU2 cross U1, as subgroups of some bigger group, you might imagine that bigger group has a single coupling constant, so it only has one value, but then it spontaneously is breaking the symmetry. There's some fields, they're called cleverly X and Y bosons, that break the symmetry at some high energy. So this energy is about 10 to the very roughly 16 GeV. Remember, the Higgs boson is down at 10 to the 2 GeV, and electrons and quarks are even lighter than that. So this is a very high energy scale. The Planck scale is 10 to the 18 GeV, so it's pretty close to the Planck scale. And this seemed in the 70s and 80s like a good idea, right? Like, the coupling constants would run, and they would unify, and not only will they meet, but we will literally unify them by saying that SU3, SU2 cross U1 are all subgroups of some bigger group like SU5 or SO10 or E6. There's different famous groups that people tried to use. So without really trying to, but without not trying to either, the way that I drew it here, they don't quite meet. And it turns out that as we got better and better data, these curves, the way that alpha 1, alpha 2, alpha 3 change with energy, depends on not only their values at low energies and not only the gauge groups they're in, but also things like what particles they couple to, the masses of those particles, and things like that. The interaction strength with the Higgs, stuff like that. So there's a bunch of parameters that you measure to calculate these curves. And in the 70s and 80s, we had measured them not so well. So to the error bars that we knew then, these curves met at some high energy. Once the 90s rolled around, we had measured these curves well enough that they no longer met. Like the precision became good, and we realized they're not actually intersecting. So but it turns out there's two attitudes you can take toward that. One is, okay, grand unification is wrong. By the way, grand unification also predicts proton decay, and we haven't measured that, so maybe grand unification is just wrong. But the other possibility is that there are more particles in between. You know, here's what we actually observe down here, like the Large Hadron Collider, okay? There's a lot of room up here in between the Large Hadron Collider and the grand unification scale. By the way, also grand unification scale, that might be the scale at which something like inflation happens in cosmology. So, you know, there's a lot of good, happy feelings, warm, fuzzy feelings about grand unification. But it didn't work in the most naive way. And so maybe one idea is that there are new particles in between the energies we've seen and the grand unification scale that affect how these different curves meet. So one simple idea is supersymmetry. So what you can do is, if you put supersymmetry at some intermediate energy scale, then you can make the curves tilt a little bit. So you get something like this, then this, and then this. And now they actually do all meet, or they would meet if I was a more accurate craftsperson. So there was this big belief in the 90s, and you know, some people still believe it today, that if supersymmetry exists at energies slightly higher than what we're able to observe, it can salvage the dream of grand unification. And without it, or without something equivalent to mess with these curves, it's harder to see that happening. It's not impossible. Nothing's ever impossible. Particle physicists are very clever at inventing models. But you notice some of the romance goes out of it, though, because if you have three lines in a plane and they happen to meet at one point, that is a non-generic thing, and that's kind of impressive. Like, two lines will almost always meet somewhere, but three lines intersecting at the same point is a special thing. Here you have three lines, but also a free parameter. You can move where you want the supersymmetry scale to be. So it becomes much less impressive that there is unification at all. And also, we haven't found any of these supersymmetric particles. Maybe we'll find them tomorrow. We haven't found them yet. So honestly, people don't know what to think about this. People don't know. Is there grand unification? Is there supersymmetry? Any of these things? These were very theoretically attractive ideas from the 70s and 80s. There's no empirical evidence for them yet, and there's been anti-empirical evidence. There's things we could have found easily. So as good Bayesians, our idea, our credence that these ideas were correct is lower now than it was 20 years ago. And by the way, this is all quantum field theory. We haven't mentioned superstring theory yet, but there was, in superstring theory, string theory, this is old-fashioned string theory. So old-fashioned string theory, there were 5 string theories, and there was one that was especially popular to be the real world, and that was the E8 cross E8 heterotic string. And E8 cross E8 were the gauge groups. So we've talked about SON gauge groups, SUN gauge groups. There are other ones. There are other continuous groups, Lie groups, that would be candidates for being gauge groups of something or another. And there's a set of exceptional gauge groups, special ones that sort of don't fit into the other classifications, and E8 is one of the best ones. It's one of the most impressive gauge groups. And string theorists didn't put it in. String theorists went through and said, what could possibly be the gauge groups of string theory? And they literally only found 5 answers, okay? And E8 cross E8 was one of them. And one of the nice things about that, one of the reasons why that was thought to be very promising, is that there is a very natural symmetry breaking pattern where you go from E8 cross E8, and you break one of them entirely, so you just get E8, and that breaks naturally down to what is called E6. I'm not explaining these at all, but I'm telling you this is true. And E6 breaks down to SU5, which can break very naturally down to SU3, cross SU2, cross U1, and sometimes instead of SU5 there's SO10 or something like that. But this is, so it was also, even though not necessary for grand unification, it was possible to fit grand unification into the scheme of superstring theory very, very easily. I said old-fashioned string theory because in the early, I guess the mid-90s, following Joe Polchinski, Ed Witten and others showed that In fact, there's only one string theory in some sense, because what we thought were 5 different string theories, and also there's another one, 11-dimensional supergravity. These are all just different limiting cases of the single underlying theory that is now called M theory. But even though that's an advance, now we know that these are all related to each other, we know very little about what M theory is, and you've heard the story probably about how there's different ways to compactify M theory to get the world, and there might be 10 to the 500 different ways. And so rather than having 5 different candidates, we have 10 to the 500 different candidates for constructing the real world out of string theory, and that's a lot harder task. So we don't know quite what to do with that. All right, we've already gone on an hour here, and I discussed the most important things. Okay, I did discuss those. But let me just do a couple of other things very quickly before going away. So, electromagnetic gauge invariance. So we talked about, should not talk and write at the same time. Magnetic gauge invariance. So I said that this is a U1 gauge theory. Electromagnetism is a U1 gauge theory. And in particular, you have something like the electron field, psi e, goes to e to the I theta, which is a function of x, because it's a gauge theory, psi e. We're ignoring spin and SU2 doublets and all that complicated stuff. But this is the basic thing that happens. This is the gauge invariance of electromagnetism. At every point, you take the electromagnetic field and you rotate it by a complex phase that can be different at every point in space. And so there were 2 very, very good questions relating this thing that I told you to things that you learned somewhere else, okay? So what about quantum mechanics? You know, in quantum mechanics, you have a wave function, and that's also capital psi, just to distinguish it from the electron field. Capital psi is a complex number, and I can imagine taking capital psi and multiplying it by some phase, call it e to the I alpha. Maybe alpha is not a good, alpha is fine. It's not the fine structure constant, just some number alpha times psi. And we know that the probability is psi squared, and that just goes to psi squared. So this is an invariance. That is to say, the probability of getting a certain outcome in quantum mechanics is unchanged if I multiply the wave function by e to the I alpha, right? Because it doesn't change the square of the wave function. So is that related? Is that the same thing? Is it similar? And the short answer is no, they're not the same thing. They're not related. But there's a longer answer. You knew there was going to be, right? So the quantum mechanical wave function, remember, is a vector in Hilbert space. If you have 2 particles, for example, well, let me say it this way. If you have a single particle in good old non-relativistic Schrodinger-style quantum mechanics, then the wave function psi is a function of position. And time also, but it's a function of the position of that particle, okay? But if you have 2 particles, then the wave function is a function of 2 copies of space, x1 and x2, right? And if you have 10 to the 80th particles, like you have in the universe, then the wave function is a function of 3 times 10 to the 80th different coordinates, 3 dimensions of space, 10 to the 80th particles, okay? Whereas this psi e is a function of x. That's it, because it's a field. It's a classical field. It is not a wave function. So this thing, when I say you multiply for the U1 gauge theory, then you multiply by e to the I theta x, that's the same x as where psi is. For every value of x, psi has a value, and the gauge parameter has a value, okay? Here in the quantum mechanical wave function, there's no equivalent of that. There's no, when you say psi at what point, it's, every different particle that psi is describing has different locations in space, so there's just no map onto that. So there's no parameter, this alpha here is not a function of space in any simple way. It's just once and for all, you can just multiply the whole wave function by a complex phase and everything is invariant. So there's a similar structure, but it's not the same thing, okay? The invariance of the quantum mechanical wave function under a single phase rotation is not the origin of the gauge invariance of electromagnetism. However, having said that, there is a relationship, and I'm not going to go into it in detail, but if you go through the details of starting with the quantum field theory wave function, and then you reduce it to the situation where you just have a single particle, electron, and then you look at the equations of motion for that particle, you can turn it into a Schrödinger-like equation for the wave function that looks like the wave equation for the electron field. It's the Dirac equation gets involved and it's very complicated. So I'm just letting you know again, if you dig into this very deeply, you will see there is a relationship, but conceptually they're very different. The relationship is not central to what we're talking about here. The phase invariance of the quantum mechanical wave function is a different thing than gauge invariance. The other question, very closely related, is what about classical, what you might call Maxwell electromagnetism? So if you've taken an electromagnetism class, classical electromagnetism, there is something called gauge invariance, but it doesn't look anything at all like this. It looks very different. So in what you have in Maxwell electromagnetism is, you have the electric field E of X, and you have the magnetic field B of X. And these are the things, the fundamental dynamical variables. Maxwell's equations tell you how these couple to electric charges, and magnetic fields are created by moving charges and that whole bit. But what you figure out, what someone tells you, or you figure out, is that you can have a vector field A called the vector potential. So I should write this as a function of X, just like E and B. And a scalar field, capital phi of X, called the scalar potential. And from these four numbers, so A is a vector, so there's three numbers, right? AX, AY, AZ. Phi is a single number, single function, so there's one number there. From these four vectors, you can derive what E and B are. And since I don't prepare for these videos, I'm not going to get the formulas exactly right. I know formulas that are correct, but they're like fancy four-dimensional formulas. The old-fashioned formulas I forget. But basically, E is like minus the derivatives with respect to space of capital phi dx plus the derivative with respect to time of A. So there's three numbers on each side. Good, that matches. And B is what we call, I'm just going to have to use some vector notation here, vector calculus here, the curl of A, which is a fancy way of saying that Bx equals the derivative of Ay with respect to z minus the derivative of Az with respect to y and other permutations. Okay, so you don't have to remember any of these. I'm not trying to explain these at a level of detail that you would actually understand. I'm just trying to tell you that they're there. But the point is, there's gauge invariance here. So I could always, in Maxwell's theory, I could just work with E and B. I can just work with the electric and magnetic fields. But even Maxwell knew that you could also rewrite them in a somewhat simpler way in terms of A and phi. So E and B, you might think there's three components of E, three components of B, so there's six numbers, six functions, right? But this little bit of prestidigitation shows you there's really only four functions that you need to derive what both E and B are doing. So they're not independent from each other. And there is gauge invariance here. So the gauge invariance in this case roughly looks like you take A and you send it to A plus the derivative. I don't know what the best notation to use here is. The notation everyone actually uses is this, grad lambda of x. So grad lambda, this is a funny notation with the upside down triangle, which means a vector, and the components of the vector are d lambda dx, d lambda, d lambda dy, and d lambda dz. So the derivatives, they should actually be partial derivatives if you're being careful, but the derivatives of this function lambda in the different directions. And there's another thing for phi, it also changes. So this is gauge invariance. This is a change in the vector potential at every point due to this function lambda that leaves all the equations invariant. You can go through, you can check that E and B don't change when you do this particular transformation. So this is what we call gauge invariance in classical electromagnetism. What does it have to do with what I'm telling you is the U1 gauge transformation? Yeah, what it has to do is lambda is the same as theta. That is to say, i.e., when you send A goes to A plus the gradient, as it's called, gradient of lambda, you send psi E to E to the I lambda psi E. That's what it is. So again, in ordinary non-field theory Maxwell electromagnetism, you don't need to worry about this because you just have particles with charge, okay? And the particles with charge don't change in their gauge invariance at all. But once you go to field theory and you want to couple everything together in a simple way, this is what you have to do. You have to actually let both the gauge field and the matter field, in this case the electron, change under a gauge transformation. But all I'm telling you here is that they really are the same gauge transformation. The gauge transformations all I'm telling you about are the same ones that we told you about, that you were told about in your electromagnetism course. And there's more to do with this, okay? So from all this knowledge, you can figure out, how you can take the fields and combine them together to get things that are invariant under gauge transformations, and that's what you need in the Lagrangian, the Lagrange density that defines the theory. So, I mean, maybe one more thing I got to tell you, okay? Maybe two more things. One is very quick, so let me just say it in words. People wanted a little bit more clarity on this claim that if you have a local symmetry, so let's say you have quarks, red, green, and blue, and you want to compare them at two different points in space, so you need to know how to transport. And the claim was if you wanted to say there was a symmetry that let you rotate the quarks independently at every point in space, then in order to compare them, you need a connection field. And that's literally what A is here. This is why the photon field is usually not called gamma in particle physics. It's usually called A because of Maxwell's electromagnetism. This is the field that you quantize in field theory for electromagnetism. It's A. In fact, what you do is, sorry, I'm telling you more than you want to know. The 4-vector potential, because of special relativity, is A mu, which is what we called phi, and then what we called A. So a 4-dimensional vector, because it's relativity, so space-time is 4-dimensional. This is the thing that gives you the photon when you quantize it. And so people said, well, what do you mean that this demand of a symmetry causes you to have a connection field in some way? So let me just confess, that's sloppy language. That's the language that we always use when we talk about these things. The more strictly correct thing to say is you have a connection field. The world has one, okay? It's not that anything forces you to do it. The way to think about it is if you wanted, in order to have a gauge symmetry, a local symmetry, a symmetry that is allowing you to do symmetry transformations independently at different points in space, then you need a connection. You need a connection field. Otherwise, you have no way of comparing what's going on at different points in space. Now, you don't need to say that connection field is dynamical. You could imagine a theory in which the gauge field is just given by God. It's just fixed. Here it is. It's not fluctuating. It's not changing over time. It's not responding to what's going on elsewhere, but it's still there. And in case this sounds crazy to you, there's a theory just like that. It's called special relativity. Okay? In general relativity, where you have gravity is dynamical and fluctuating, the connection field changes from place to place. It has dynamics. Einstein's equation is what gives it to it. But in special relativity, there's still space-time. There's still a way to compare vectors at different points in space-time. In other words, there is a connection, but the connection is just given. It's just fixed, and it's flat. The curvature of it is 0. So there's no necessity that comes along with having these fields. You do experiments, ultimately. When you want to say, like, people ask, well, why is it SU3 cross SU2 cross U1? You do the experiments. You do particle physics, and you say that's what's needed to fit the data, right? And they say, like, well, if you have 3 quarks, how do you know there's 3 different... If there's 3 quarks in a proton, how do you know there's 3 different colors? Well, as we will see, there's something called the Pauli exclusion principle. 2 fermions, like quarks, cannot be in exactly the same state. But it turns out that the 2 up quarks, let's say in a proton, basically are in the same state. How is that possible? Well, one of them is red and one of them is blue. Or anyway, they're 2 different colors. So they're not really in the same state. So we know that we need these different colors in order to make sense of what goes on in protons. So all of this is driven by data. All of this is driven by trying to understand the actual data. That's the only real reason we know that these fields exist, because you need them to fit the data. And the final thing is, let me say, again, a little bit more detail than you want, but one more little connection between gauge fields and curvature. Remember, so we said that if you have a gauge field, you can parallel transport. You can parallel transport vectors in some generalized sense, like a quark with its color is like a little internal vector. And parallel transport lets you define the curvature of that gauge field. And we talked about the Riemann tensor. And depending on whether you watch the Q&A video, one way of writing the Riemann tensor is R rho lambda mu nu, but it's a map from 3 vectors, v1, v2, v3, to a 4th vector, v4, and the map is this little thing. I'm not going to go through all the details, but v1, v2, backwards, minus v1, minus v2, and then if you have v3, it gets changed by an amount v4, okay? So that's what the map is. And so you might say, so there's 2 questions here. Can you have, there's a lot of questions here, sorry. Can you have 0 curvature? Can you have a connection without curvature? Can you have a connection which is flat? The answer is absolutely yes. And that would be special relativity, for example, in space-time. So the connection, this is the Riemann tensor. What I didn't tell you is that there's something called the connection. I told you there was something called the connection, but I didn't tell you the formula or the symbols. The connection looks like this: gamma lambda mu nu. Okay, and this is roughly what tells you, so the Riemann tensor tells you how does a single vector rotate a little bit when you go around a loop defined by 2 vectors. Roughly, the connection is saying if I just have a single direction that I'm moving in, okay, v1, and then I have a vector that I am moving, v2, and I move it a little bit, it sort of changed infinitesimally, okay, compared to where it was, and that's v3. So that's why there are 3 indices on the connection. And the way, so there's a connection tells you how to transport in one direction, but that just depends a lot, you know, the details, the actual equations depend a lot on what your coordinates are and what direction you're moving in, etc. Whereas the Riemann tensor is what we would call gauge invariant. It is independent of your coordinates or anything like that. It's a much better defined thing. And to get to the question that was being asked, there are exactly equivalent structures in the gauge theories for internal symmetries, like SU3 cross SU2 cross U1. So for SU3, instead the connection, sadly, we still use the letter A, whether it's SU3 or SU2 or anything. We would write A mu AB. Why do we use different letters? Why is, you know, the connect, so for the Riemann tensor and the space-time connection, the reason why gravity and space-time are harder or more interesting is because it's only space-time. There's only vectors that literally point in directions. So the question, what about the vector you're moving, and the question, what direction are you moving it in, are questions being asked relative to the same space, namely space-time. Here, when you have an SU3 connection, you're still taking a direction in space-time, v1, okay, but you're saying I'm moving a quark field, so let me draw it in a different color, Q, and that gets moved to here under parallel transport, so it changed a little bit, and I want to ask by how much does the quark field change? So these indices A and B are quark indices, or really SU3 indices. And so now, unlike in The Riemann tensor and space-time case, where all the indices are in the same direction, or in the same space, up, down, left, right, forward, backward, past, future. Here, there's indices in color space, which are A and B, and an index in space-time, which is the direction you're parallel transporting in. And there is curvature, SU3 curvature. And roughly speaking, we call that capital G. Oh, I shouldn't call it capital G. Let me call it capital F, mu nu A B. And yeah, it's complicated, sorry, but I gotta tell you what it is, because I started, so I shouldn't stop. It is the derivative in the mu direction of A nu AB minus the derivative in the nu direction of A mu AB minus or plus, I'm never going to get it right, how am I going to get this right? A mu A C A nu C B. Let me call that plus, and then minus A nu A C A mu C B. Whew. Something like that. This is a very close approximation of the true thing. Anyway, the point is, there's an absolute parallelism. From the connection in space-time, you can construct the Riemann tensor. From the connection in the gauge theory, SU3, you can construct this curvature tensor. And from this curvature tensor, you're going to make the equations of motion for the gauge field. So for electromagnetism, for example, I think I might have said this already. For electromagnetism, F mu nu doesn't need to have any indices because it's just a single complex number that is being moved around. There's no indices. It's not like SU2 or SU3 where there's 2 or 3 different directions. There's one direction. So F mu doesn't need any indices for E and M. It's just a U1 gauge field. And it all circles back. This is, there are zeros. It's a 4x4 matrix. Zeros on the diagonal. How do you know that? Because if you look closely at this formula I wrote down, it's anti-symmetric in mu and nu. So whatever the value of F mu nu is for one value of mu and nu, when I switch mu and nu, it better be minus that. So this is F0, 0, F1, 1, etc. So if I switch 0 and 0, I get 0 and 0. So the number that is equal to minus itself is 0. So all these diagonal elements are exactly 0. Okay. And the top line here, I never get the minus signs here right, but this is the electric field. EX, EY, EZ, minus EX, minus EY, minus EZ. And these other 3 empty slots, the magnetic field. BZ minus BX, BY minus B. Nope, I didn't get that right, did I? I mean, I had a good chance of getting it right, just didn't quite see. That's BY, this is BX. I'm not getting the signs right, but I do want to get the indices right. This is minus BX, this is BY, this is minus BZ. Anyway, way more detail than you need, way more detail than you can possibly follow. All of this is to say that the good old-fashioned way of doing electromagnetism that Maxwell would have recognized is still here. It's still there in this fancy-dancy language of connections and gauge fields and things like that. They're all related to each other. And, you know, I'm not giving you enough information to understand all these indices, but it's actually pretty understandable. Like, it's way easier than quantum mechanics, to be honest. So if you can find a good book on classical gauge theory, I'm not sure if there is one, but I think Valery Rubikov wrote a book. It's a big, hard book, but it's called Classical Gauge Theory. That's one. But anyway, gauge theories are worth learning about. They're really interesting. There's a lot going on. I have many, many more things that I could say, but, you know, ars longa vita brevis. We have other things to do. So thanks for sticking around with this one. This was a long, complicated Q&A video, but it's worth it. This is important stuff. This is how the real world works.